Welcome back. Today we'll be continuing our coverage of the fundamentals of engineering mathematics topic of differential equations. So far we've looked at how to categorize differential equations and how to solve first order differential equations. And if you need a refresher on that, check out those videos. Today we're going to cover second order differential equations. Normally, on the FE exam, you're only going to have first or second order differential equations to solve. So we can see the steps we're going to follow here. They are the same as the steps we followed for a first order differential equation. So here's our equation. First thing, as always, that we want to do is categorize it. So if we look here, we see our highest derivative is our second derivative. So this is a second order differential equation. All of our derivatives are taken with respect to the same variable. We can assume that. We don't see the variable there, but it's either dy dx or dy dt. So this is an ordinary differential equation. And none of our derivatives are raised to a power, embedded in a function, anything strange like that. So this is linear. And if we look at our coefficients, we could see coefficient here is 1. These are all scalars, so it's constant coefficients. And our forcing function over here on the right is 0. So this is a homogeneous equation. So now that we've categorized, we can go to our handbook, and what you see here is a copy of the handbook, and we can go to that categorization. So we have a second order linear homogeneous differential equation with constant coefficients. And now we can just follow the prescribed procedure from the handbook. So first it tells us to put the equation into this format. Then we're going to make a characteristic equation and solve for roots. And then, based on the values from the characteristic equations, we can decide if this is an overdamped, critically damped, or underdamped differential equation. So a little bit more complicated than our first order, a little bit different, but we'll see how to work through it. So first, format. We want to look at the format in the handbook and make sure that our differential equation is formatted that way. Taking a quick look, we can see that it is already formatted that way, so we got lucky here. But remember that the coefficient in front of the highest order derivative should be 1. So we can see that it is 1 in this case, but had there been a different term here, we would have had to divide that out amongst all of the derivative forms to get this equation to work correctly. And if we match up terms, we could see that our a value is 4, and our b value is also 4. So now we want to determine the homogeneous solution. We want to do that first by writing the characteristic equation. So r squared plus ar, we just said a was 4, plus b, which we just said was also 4, equals 0. And now we can solve for the roots of our characteristic equation. So negative a, negative 4, plus or minus the square root of a squared, so 16, minus 4 times b, so minus 16, over 2. And we could see that the radical term here will be 0, and we'll end up with negative 4 plus or minus 0 over 2, so negative 2. And anytime you end up with a single value, it means that both r1 and r2 are that value, so we have a double root, negative 2, negative 2. So now we want to make a determination on which of these three options we have. So are we overdamped, critically damped, or underdamped? And how we'll do this is by doing a comparison between a squared and 4b. We want to see if that's greater than, equal to, or less than. So a squared, 4 squared is 16. 4 times b, 4 times 4 is also 16. So we could see that they are equal, and we are critically damped. Now we could have figured that out just by seeing that we have a double root here. Anytime you have a double root, you're going to be critically damped, but doing this comparison is always good. So now that we know we're critically damped, we want to go to the critically damped solution, which is C1 plus C2 x e to the root, which is negative 2, times x. And remember that C1 and C2 are constant values that can be determined using initial conditions if you have them. This particular problem doesn't have initial conditions, so this is the furthest we can go to solve it. Had you been provided initial conditions, you could solve them using the same approach that we used for the first order differential equation with initial conditions. So again, to summarize, we first categorized our equation, We went to the handbook for that categorization. We matched the formatting that the handbook requested. We used the solution that the handbook pointed out by first creating a characteristic equation, then solving for its roots, doing a comparison of a squared to 4b to pick between under, over, and critically damped, and then we wrote our homogeneous solution. Now, had we had initial conditions, we could have found coefficients, but we didn't have that here. Had we had a non-homogeneous equation, we could have found a particular solution, but again, we didn't have that here. Enjoying these videos? Follow the links in the description below to find out how you can reach out for personal tutoring. Like and subscribe to get notified when new videos drop, and comment with suggestions for future topics.